Okay, so I'm going to make this video a close-up of all the rocks that I mentioned in the other videos so I can show you them more closely. Alright, so let's start with, move some of these out of the way. This is my stone bench here that I made in my garden. Very convenient for a table. Alright, so let's take a look at this granite. So let's zoom in a bit. And what we see, like for instance here, this is a potassium feldspar, K-spar crystal. This, I should have brought a pointer with me, but these white ones, that is plagioclase. And then if you look, like right in here, it looks like there's some gray, little clear grains. That's the quartz. There is some biotite, that black one. There's some biotite. And there's probably some hornblende mixed in more of the black grains. But it's mostly coarse grained. You can see just about everything that you would need to see to identify it. So that's a coarse grained granite that has a lot of potassium feldspar. That's why it's pink. This one has much less. In fact, it may not have any, at least on this side. The other side is the one with those large potassium feldspar crystals. So there's these really big ones, but they're not mixed throughout the entire rock. So there are some areas that have no potassium feldspar crystals. So if we look on this side, it's pretty white, but all the white or kind of yellowish white, those are all plagioclase feldspar, plagioclase crystals. The darker gray ones are quartz, and then the black are biotite and or hornblende. And we can see in this one there's not a whole lot of those dark grains. The interesting thing when you're estimating without a comparator is you might say that there's an awful lot more dark minerals in there than there actually are. That is very common. Your eye notices the dark much more, and so it overestimates how much dark minerals are present. So that's granite. We can see in this granite, this is a beach cobble I found. It looks kind of like an egg. That's why I picked it up. Let's see, let me get it wet here. You can see it a little bit better. It kind of brings out the color here. But all of the light, all of that white, that's plagioclase again, and there's some like little gray bits. I don't know if you can see those. Get in focus here. Those are quartz, and then there's the biotite and hornblende as well. Now, unfortunately, I do not have a gray rhyolite. As I mentioned, I only have the pink one, but we can still take a look at it. And this pink one is porphyritic because we can see those larger crystals. There's larger black ones, larger white ones, but not all rhyolites are porphyritic. They're mostly not. Actually, most of the ones that I have are not porphyritic, but this one I got in Arizona and quite like it, so I brought that one home since it's mine. And that is a typical rhyolite, light colored, pink or light gray. Okay, now let's go on to diorite here. Let me get this one wet so we can see it. So with this one, again, it's nearly 50-50 light and dark. The dark minerals are hornblende. The white minerals that are really blowing out here on my camera are plagioclase. So 50-50 light and dark. Let's see if we can zoom in anymore. Well, let's see, do it this way. And you can see a little better. So we can see those crystals, that they are, we got plagioclase and hornblende. They are large enough that we call it coarse grained rock. This one, this is from Mount St. Helens. This is an andesite. It is porphyritic. We can see the larger plagioclase crystals as well as some hornblende, the black ones. They often are rectangular because hornblende is often rectangular. Now they are weathered a little bit in some places, so they are slightly discolored, but that's if we had a very, very fresh surface, like if it's not on a fracture or something, they'll be really they'll look a little bit more pristine. And this is another one from Mount St. Helens. It's not as obviously porphyritic. In fact, I would not call this one porphyritic. It is a green gray. This is blowing out the color there. There we go. That's a good color. Well, actually, it's a little too blue, to be honest with you. But it is a green gray, very light, very fine grained. And if we were to analyze this, it would be roughly 50% plagioclase, 50% hornblende. So that makes it an andesite. And the andesite, if you haven't guessed, is named after the Andes Mountains because it's one of the more common types of rocks found in, or volcanic rocks found in the Andes. And of course, if you remember, off the coast of South America is a subduction zone. So the Andes are a volcanic mountain range that are the result of subduction of the Nazca Plate underneath the South American plate. All right, so next let's look at, let's move these out of the way. Let's look at gabbro here. And hopefully, as I turn this in the light, you'll see that those crystal faces will flash at you so you can see how big they are. These are not fine grained, even though from a distance it might appear to be uniformly black. Those crystals are in fact larger than 1 millimeter. And then we've got the plagioclase mixed in here. It's not a lot of plagioclase, but there is some. And that gives us the mineral composition for gabbro of mostly dark colored minerals, lots of plagioclase, there's probably some olivine in here too, so we've got mostly ferromagnesians with a small amount, 20% or so, of non-ferromagnesian, in this case all plagioclase. There wouldn't be any case bar in here, and there wouldn't be any quartz. Those form at much lower temperatures than gabbro does. Next is the partner rock here, basalt. This is that pillow basalt. You can see the kind of the rounded shape here. That is the pillow, and of course we see barnacles stuck on it because it was in the ocean before I got it. But this one is fine grained. They can be solidly black. They can be lighter black, sort of a grayer color depending on composition, and if it's got a little bit more plagioclase, more of that, towards the 20% end versus a little bit less than that, then this one will be a little bit grayer than it will be black. But they're often black right at the beginning, but something like a pillow basalt is often slightly altered when it's injected into the seawater, so it's, in this case, it's green. And it's also been jammed down into a subduction zone and then stuck up onto a continent and lifted up to the surface. So this poor rock has been sufficiently stressed. It has a nice life now sitting here with me, but it did have a very difficult time in the past. And this one is vesicular basalt. It is a basalt, so there are pyroxene crystals in here. There's plagioclase crystals in here. They're just very, very tiny. And as the gas was coming out of the magma, those bubbles solidified, and we end up with these frozen gas bubbles here, which makes it a vesicular basalt. So it's not glassy, does not contain volcanic glass. It is a rock. It has minerals, but it has those frozen gas bubbles that makes it vesicular. And here is a porphyritic basalt. So we've got the very fine grained background and the chocolate chips, if you will. So we've got the cookie and the chips. Fine grain tells us that it had to be erupted on the surface or very near the surface as a volcanic rock. And the large crystals, the plagioclase crystals in here, simply tell us that this rock was crystallizing, or this magma was crystallizing before it was erupted near the surface. So we get 2 stages of crystallization, 2 stages of cooling, rather than just one, if it was all uniform size crystals. Right, last one on our continuum here, from lighter colored to darker colored, less ferromagnesians to 100% ferromagnesian. So we've got the we have the green olivine crystals and the black olivine crystals, and olivine is a ferromagnesian rock. This is a mineral. This is almost entirely olivine. There is not much else mixed in here. So it's almost 100% ferromagnesian minerals. This is the mantle. So this is not something that we're going to find brought up to the surface as a magma. It is not going to be a magma that cools at 8 kilometers below the surface. This is something that is present in the mantle and does not come to the surface unless a chunk of it is ripped off of the mantle and brought up with magma as it comes up to the surface and preserved in that new igneous rock as a xenolith. So these, and you can see the backside of this. It's not crystalline. This is a probably a reaction rim. So this was reacting with or a melting rim. Was reacting with the magma that it was encased in before it was solidified. So when they break open, we can see the olivine on the inside. But this is not taken from a chunk of the mantle at the surface that we found it and could take off pieces of it. Rather, this is a xenolith that was brought up by magma and preserved so that geologists could see it. Otherwise, we'd never know what the mantle looks like. We have actually never been able to drill to the mantle. We cannot even drill through the entire oceanic crust. Every time, it's very difficult to drill in the ocean, first of all. Second, just because you're in the ocean. And the other problem is the rock is very, very hard. And to get through even the oceanic crust, you have to drill down through very solid rock, 6-7 kilometers through that to get to the mantle, and it's just too hard, too expensive. And when I say hard, I mean both literal and figurative. So literal, the rock is hard, it just chews up drill bits left, right, and center because it's very resistant to abrasion, and then it's hard because it's very difficult. So those two things. So the only way that we know what the mantle is composed of is because of these xenoliths, as well as seismic studies that can give us information about how earthquake waves travel through the mantle, and it gives us information about what minerals are present, what type of rock is present. All right, so that should help. Oh, and I forgot to go through these last ones. Those were the crystalline rocks. So now I got my weird volcanic. So here is, put it the way, right side up. So this is mahogany obsidian, so it's glassy, you can see the shine. It also has conchoidal fracture that was in your mineral lab, but if you look, you see these curved surfaces, and if I turn it this way, hopefully you can see that this surface is curved. That conchoidal fracture is very common in volcanic glass and obsidian. It's also common in regular glass. We also see it in a sedimentary rock called chert, so it'll come back again. We also sometimes can see it in coal, but most of the time where we see it is in obsidian and in chert. Another name for chert is actually flint or jasper. This, because of the conchoidal fracture, it will form very thin edges, and sharp edges can be used for arrowheads, spear points, and that. In fact, I've cut myself on this rock, running my hand along the edge by accident. I end up getting cut. So these are where obsidian is present. Stone Age people would turn them into points, either spear, knife, scrapers, arrowheads, that sort of thing. So that's with the glassy texture. Here is pumice. You can see those holes a little bit better here, hopefully. This is frothy volcanic glass, so there's no minerals in here, but you can kind of think of pumice as being like if you had if you froze a soda. So you shook up soda and it had a froth on the top, and then you froze it. That froth at the top of your soda that is now solidified ice, that is what like pumice is. Only unlike ice, which has a crystal structure, this has no crystals. It cooled too quickly for any minerals to form. So that's pumice, vesicular texture. And then I've got my two airfall tuffs here. Let's look at this one first. And we can see individual rock fragments. There's a rock fragment, rock fragment, rock fragment. This is a hole. That was most likely a rock fragment that got plucked out. It got knocked out. There's a pumice fragment, lots of little bitty rock fragments. So this one, the volcano blew up. All of the white or light gray material in the background, that's all volcanic ash. And volcanic ash is just volcanic glass shards. So this one contains volcanic glass just like the others two, obsidian and pumice, but it also contains anything that's blown out of a volcano. There could even be some early formed crystals. Think of that porphyritic texture. If that was occurring in the magma, then when the magma erupted and blew out, then those early formed crystals could also be in there. So the one thing that all tuffs have in common is they have ash, lots of volcanic ash. They may have rock fragments, they may have pumice fragments, they may have early formed crystals, but no matter what, they will have ash. So that's a gray tuff. Here's a pink tuff, also possible. It has some pumice fragments in here. They're kind of squashed pumice fragments. There may be some early formed crystals. There's some black little dots. Those may be early formed crystals. And so two things that are common in addition to the rock fragments are and the pumice fragments are those early formed crystals. So all of the pink that you see in here, that is all volcanic ash. So there's no, it's not mineral, there's no minerals in it. These are, well, the ash has no minerals in it, but there could be minerals because if there was any in the magma that blew up, then they could be included in here. I always say that for tuffs, if there were cows living in a volcano and the volcano erupted and the cows landed, they would be in tuffs. So they're kind of a garbage can rock. If anything that blew out of the volcano lands on the ground and is and forms together as a rock, becomes a tuff. So those are the weird volcanics: pumice, obsidian, and tuff.